Welcome to BKW Physics. I'm Mr. McConley, and today's topic is scalars, and more specifically, or more detailed, is the vector part of it. So first of all, we got to know the difference between what's a scalar and what's a vector. If you have something that's a scalar, it has a magnitude. And a magnitude, is that still a 9 magnet?
Yep.
9? Yeah, 9. And a magnitude is a size, it's a number. So like you might say 50 meters per second, in example. 50 meters per second is a magnitude, it's a scalar. Well, a vector is very similar in that it has the magnitude, but you add to it a direction. So now you would say like 50 meters per second at 20 degrees, and now you're stating how fast at a certain angle, and now you've made it a vector. So vectors, the bottom line is the direction matters. The direction is key. So when we were doing other chapters, when we talked about velocity, we said the direction of a velocity matters because this is 20 meters per second and this is 20 meters per second, but they can't both be 20 meters per second, so one of them's got to be negative and one's got to be positive because they're vectors. Acceleration, like when you drop something, gravity always pulls it down at a negative 9.81 because it's a vector. So vector scalar, that's the difference. Some of you already got that, but moving on today, we're going to talk more. How do you use vectors? Well, a vector actually can be shown by an arrow. This is drawn with a ruler. It has a tip and it has a tail. It's supposed to look something like a, like a bow and arrow. So, bow and arrow, there's the tail and the tip. And if you're trying to say this is vector A, you put the letter A, but you also put a little whoop over top of it. Can you see that? It's like a flat line with a little check on it. That is the symbol, the way you symbolize saying I am talking about that vector. So vector A, or you might be saying, oh, this is vector B, whatever. So that's the way to write it. Now when we get into actually using the vectors, we could do something like this. We could add them. And when we add them, you might say, okay, I have two vectors, a 300 and a 400. Like I walk 300 meters, I stop, and then I walk 400 meters. How do you represent that with vectors? So if I walk 300 meters, I could take out my centimeter ruler or whatever and say 1, 2, 3 centimeters, 300 meters. Okay, so you would want to have some sort of a scale. And my scale might be that 1 centimeter equals 100 meters. Okay? So I have a scale of 1 centimeter is 100 meters, so I draw 300 meters, and I said I walked, I stopped, and then I walked 400 meters more. So how do you show that? Well, you start a new arrow, and you go 1, 2, 3, about that long. So that's, of course, I would be doing this with a ruler to get it perfect, but boom, there we go. I walked 300 meters, I stopped, I walked 400 more meters. And usually what you're looking for when you are doing these vector problems is what's called a resultant. So the resultant would be, and the abbreviation for resultant is a capital R with that little symbol over the top again. The resultant would be what in this case? 700 meters. Okay? On my scale, it would be 7 centimeters more. Alright, that's easy. We could do the same with a subtraction type of problem. If I said, for instance, maybe someone was pulling with 9 newtons, and then someone else was pulling the opposite direction with 7 newtons, how might you draw that? Well, you can say, okay, again, I can say 1 centimeter is equal to 1 newton, like that. So I can draw 9 newtons going this way. That'd be 9 centimeters long. Then, I guess I'll keep the I better change colors, so this is going to be hard to see. So then 7 newtons is pulling the opposite direction. And you're tempted to want to do this, right? Draw the 7 this way. You're tempted to want to do that. It's not really the way you want to do it. What you want to do is you want to start from where you just left off. So if the problem started right here, hold 9 this way, now you're right here, you want to come back 7 this way. Okay? You don't want to pull the opposite direction. Makes sense, okay? So what's our resultant? With 9 this way, you pull 7 back this way, our resultant is 2 which way? 2 in the way that's stronger. 9 is stronger, it wins. 2, so our resultant, bar with a little mark over top, is 2 newtons. And you can see that the arrow is pointing to the right. Okay. So that's adding and subtracting. Then you might get into something where, let's say you walk 40 meters east, and then you walk 40 meters, walk 40 meters east, 20 meters north. How about that? So, there's my 40 meters in the east direction. I just want east to be to the right because it seems like it should be. And then I'm at this point, so from this point, I'm going to go 20 meters in the north direction. So where's my resultant? Because they don't seem to like overlap one another like the other two problems did. Yes? Diagonal. From here, we're starting from here. Like where does the arrow, the tip of the arrow have to be?
Probably starting there.
Because ultimately, if you think of it like two people pulling on something, if one person pulls this way and the other person pulls this way, the object's going to kind of move that way. Okay? So that's the way your arrow should point to represent that. Or you can think of it as when you draw a resultant, it's like the shortest route. Like if this was walking down the street this way and then walking on the street this way, this is like as the crow flies. So resultants are the quickest way to get the job done. So my resultant would be, now you have a little bit harder problem. You can do it two ways. If you had drawn this to scale, like literally if this was drawn to scale, you could measure, and you'd get the right answer. Because if you draw it to scale, it would be fine. But I didn't really draw it to scale, so what would I have to do?
Agree.
Yeah, a squared plus b squared equals c squared. And then that would give you your answer. We don't have to do that right now, it's not working. You can also get into problems where if one person pulls, let's say, 50 newtons at 0 degrees, that's that way. And another person is pulling 30 newtons at 30 degrees. Okay, what do you do with that mess? Well, the first issue you might see is that these two vectors are really not connected the right way. You know what I mean? Like I've always drawn each picture where the tail of the one arrow connects to the tip of the first arrow, you know, and it's not drawn that way. So that's the first thing you can correct or change about this. Right now these are tail to tail, and that's a problem. I don't want that. So you got to fix that by making it tip to tail. So which one do you want to leave alone and which one do you want to move?
The 0.
Want to move the smaller one or leave the smaller? Move the smaller.
Well, maybe you should do
I don't care at all. This is fine with me. So I'm going to use this little yardstick to help us represent here. So, boy, that line's not very straight now that I hold it up there, but that's okay. So anyway, this is pointing this way. So it has to continue pointing that way, and it has to continue remaining the same length. But it has to be connected to the end of this. So basically what you're going to do is go and move that over. Okay? So it's going to end up down here, it's going to be 30 newtons at 30 degrees. Now it's correctly, connected tip to tail wise. But the way you actually have to pull that off in reality, because I just did it kind of like freehand, is you would have to lay down a protractor here, get your angle, lay down the protractor here, repeat the angle, and then once you got the angle correct, now you can just measure your length because you drew it to scale and you can get the right length. Yeah?
If you gave us the angle, do we have to use the protractor on that?
Oh, no. If I gave you the angle, then you could just go from there. Okay? But if the angle wasn't given, like you didn't really know, it was just 30 newtons, you can measure the angle, pull it over, tack it on there. Now, where's the resultant on this thing? Well, you're kind of ignoring this one. You don't have to erase it in your notes, but you're ignoring that one now because you moved it over so that you could correctly add them. So it's from where you ended up. Some people are getting the system here. And this one would definitely require either drawing it to scale or doing some more heavy-duty math to get that answer. So we could figure that out. All right. The last thing I want to show you, kind of neat, is if I need some space here to get this done, so let's clear up an area. If I have three vectors, let's make them A, B, and C. And I decide to add three things together. Well, right now they're all tail to tail. I'm going to have to shuffle some things around. So what do you want to leave alone first?
C.
Okay, we'll leave C alone the whole time. And we'll tack on A and B. So the first thing I want to do, and I'm going to do this all freehand, it won't turn out perfect, but you'll get the concept. I'm going to take B, and I'm going to slide it down here, noting that I have left it the same length and left it pointing in the same direction. So I've kind of like done that. Now I'm going to take A and move it down here. Hopefully that's close enough representation. Now I'm kind of ignoring that, right? What's my resultant? Well, my resultant is there. Okay, that's neat and everything. But let me do it one other way for you. What if I had left B alone? B was the one we were going to leave alone the whole time. So my problem would have B like this, right? And now we'll slide A over. And then we'll tack C on the end. Now, my resultant is from where I started to where I ended up. And what do you notice about those two resultants? They're the same. It does not matter which order you add vectors in. If you add 3 vectors or 4 vectors, no matter which order you add them in, as long as you do it tip to tail, you will get the right answer. And that's a key of adding vectors. So for today, physics.